This video is about the ideal gas law. Combining Boyle's law, Charles' law, and Avogadro's law can give us the ideal gas law, where we bring all these ideas together. Each of those other laws, Boyle's, Charles, Avogadro's, Gay-Lussac's, they were about a set of initial conditions and a set of final conditions. But the beauty of the ideal gas law is that you can determine any one of the four gas variables, if you know the other three, at one moment in time, one snapshot in time, or one set of conditions. So you don't need initial and final conditions. In one snapshot in time, if you have pressure and volume and temperature, we can calculate the number of moles of gas. So if we have three of the variables, we can calculate the fourth out of P, V, N, and T. So that makes the ideal gas law pretty cool. Ideal, one might say. Now, the ideal gas law uses this constant R. And so R has a known, a calculated gas law constant, 0.0820057. And its units are, I think I'm going to just move me here. Its units are liter atmosphere over moles times Kelvin. So it's got this 4-part unit for really the 4 variables. I often find myself simplifying this to 0.0821. Just in case I do that, know that I think that's a close enough approximation. Just like I often say that, you can convert to Kelvin by adding 273 to your Celsius. It's usually a good enough approximation for almost all of our problems. So again, this R is a constant, it's kind of like the speed of light or the gravitational constant. This is a known measured constant. So the conditions of 0 degrees Celsius, which is 273 Kelvin, see there I go, just cutting it off at 273 Kelvin, and 1 atm are called standard temperature and pressure, STP. So when we say, hey, this problem is at STP, we mean at that standard temperature of 0 degrees Celsius or 273 Kelvin and that standard pressure of 1 atm. So this example says, what is the volume of 1 mole of a gas at STP? So we know N equals 1 mole. STP means we know pressure is 1 atm, and we also know that temperature is 273 Kelvin. So we can try using the ideal gas law, using PV equals nRT. Now this says what is volume? So we don't know V. We want to solve for V. We're going to want to isolate V and get it alone. So we could isolate V by dividing both sides by P. Okay, so we divide both sides by P. We get V is nRT over P. Okay, well our N was 1 mole. We know R is 0.0820057. I like to include all of its units. I really suggest that you write down liter atmosphere over mole Kelvin because we're going to cancel out the units we don't need. And we're going to multiply by 273 Kelvin. And then we're going to divide by the standard pressure of 1 atm. I'll show you what I mean by those units. Kelvin cancels with Kelvin. ATM cancels with ATM, and mole cancels with mole. So all of the units of the gas constant have canceled out except liters. And that's great because I was solving for a volume. So my volume is going to be in liters. So try all that in your calculator. I think it's a really good idea to give this a try. And for a volume, you should get 22.4 liters. Now this is a special number. It's the molar volume. 22.4 liters is the volume of 1 mole of any gas at standard temperature and pressure. 22.4 liters. So about what does that look like? It's about the size of a basketball. I'll have to clear this. It's roughly the size of a basketball, a little bit more. So if you're wondering about molar volume, this is 1 mole of any gas at standard temperature and pressure. So that just gives you a good idea of what it actually looks like. Okay, let's look at some molar volumes of some real gases. So we talk about ideal gases, real gases at 0 degrees Celsius and 1 atm. Hydrogen has a molar volume of 22.43 liters, helium 22.41 liters, ammonia 22.4 liters, nitrogen 22.4, fluorine 22.38, pretty much 22.4. Argon, 22.09, carbon dioxide, 22.4, again, great. Chlorine, 22.06. So we see a few that are a bit of an outlier, but this is a pretty good approximation, this idea of molar volume. Okay, so the ideal gas equation can actually be modified when we're calculating, various changes in condition, ones and twos. So if we solve for R, so let's say that we take PV equals nRT and we solve for R. To do that, we'd have to divide both sides by N and T to isolate it. So to isolate R, you divide both sides by N and T and you get PV over NT. Ooh, PV over NT. I don't like that. Okay, so we can do, sorry, I'll get rid of that line. It's PV over NT. We can do that for initial conditions. P1 V1 over N1 T1 equals R. We can do it for final conditions after a change. P2 V2 equals N2 T2 after a change. Well, we know that R equals R. We can actually set these equal to each other. So we can set P1 V1 over N1 T1 equal to P2 V2 over N2 T2. Basically, we could be changing, in theory, all of the gas variables, and we could figure out, what one of the new gas variables was going to be if we were changing the others. It allows you to change multiple gas variables and look at initial and final conditions. That's kind of the short story I was trying to say there. Okay, so let's look at what would this equation become if the amount of gas does not change, if N is constant. So let's set up the whole equation again, but let's say that N is going to be constant. If N is going to be constant, N is equal to N on both sides of the equation, and we essentially cancel that out. And so we get P1 V1 over T1 equals P2 V2 over T2. So we could use that if pressures and volumes and temperatures were changing. So it kind of expands on, Charles and Boyle's law, which just let you look at 2 variables at a time. Now we can look at 3 variables at a time for our gases. What would it become if, say, amount of gas and temperature are constant? Let's take a look at that. Okay, so if amount of gas is constant, the N's are constant. If temperature is constant, the T's are constant. We will get P1V1 equals P2V2. Wait a second. Have we seen that before? Do you know what law that is? It's Boyle's law, right? That one we know as Boyle's law. So we can derive the other gas laws actually from this, what we call a combined gas law. So I would really say that these are different combined gas laws. What about this last one? What does the equation become if pressure and temperature are constant? So what if we slashed our pressures and we slashed our temperatures? Well, then we get V1 over N1. I'll just squeeze it in. V1 over N1 equals V2 over N2. Well, have we seen that before? V over N equals V over N? Yeah, that's Avogadro's law. Avogadro's. Not spelling the best. That one was Avogadro's law. So we could actually derive all of the other gas laws We could derive Gay-Lussac's. We can derive Charles' law. You know, I mean, how do you get to Charles' law from here? Well, you hold the pressure is constant and you get volume over temperature equals volume over temperature. You can derive Charles' law here too. Here, I'll put it over here. It's just as easy to do that. And so we could just keep this up. We can derive them all. There's Charles' law. Okay, so what do we call laws like this? The P1V1 over N1T1, or even P1V1 over T1 equals P2V2 over T2. If we have 3 or 4 of the gas variables all combined, we refer to these as combined gas laws. Different ways of having the combined gas law, but just we've got more than just 2 variables at stake here. We've got 3 or 4 variables, and so we'll call those versions combined gas laws. But it's kind of interesting because all the individual gas laws can be derived from the combined gas law. It's really pretty powerful. Okay, next up, there is density to consider. These gases have varying densities. We know that density is mass divided by volume. So the density, or mass divided by volume, of a gas is an important property that we can use along with its molar mass too. We know different gases have different molar masses. So here we're going to use kind of our fancy M for molar mass. We're going to use the ideal gas law, and we can come up with equations for density and molar mass. So another way of looking at this, for example, is to look at these different gas laws and try to sort of rearrange them. For example, we can say, well, density is mass over volume, and we can start rearranging. Like we can come up with equations for just the density as pressure times molar mass divided by the gas constant times temperature, or molar mass we could come up with as density times the gas law constant R times temperature divided by pressure. So different ways of looking at these. Here are a whole bunch of variations on the different gas laws. We can derive these by using algebra to isolate a variable, but this is just a big table of gas laws to make it easier for you to find the one that might be most useful for you for a particular problem. And so just to remind you, PV equals nRT, well, that's your ideal gas law. P1V1 over N1T1 equals P2V2 over N2T2. That's your combined gas law. And then, you know, basically we've just got other derivations or like, you know, ways that we've rearranged the algebra for you that might be helpful for you to use in problems. So kind of just trying to be nice and hope that it helps you through the algebra portion of these problems. Okay, so we've got some practice. What is the density of chlorine at 298 Kelvin and 0.5 atm? So, you know, probably one of the best things to do is go back to our equation. And we had an equation. It said density is pressure times molar mass divided by R times T. So just using one of those prior equations and using it to our advantage. Okay, so we know pressure is 0.5 atm, so we can plug that in. 0.5 atm. That M, that's molar mass. We'll have to go to our periodic table and get that. We know R, the gas law constant, is 0.0821 liter atmosphere over mole times Kelvin. And we know that temperature is 298 Kelvin in this problem. Okay, let's go get the molar mass. Take a second to find your periodic table. Find chlorine. It's 35.45. But there are 2 of them. So this is going to be 70.90 grams per mole for a molar mass. So let's put that molar mass of 70.90 grams per mole in our equation. Okay, let's cancel some units. ATMs cancel with ATMs. Here we've got Kelvin on the bottom on our denominator here, and we've got Kelvin. So Kelvin cancels with Kelvin. Here we've got gram per mole and gram per mole, so those are going to cancel. And lo and behold, we'll have a density in grams over liters as our remaining units, which are great because that's a density unit. Maybe not one we're used to seeing, but it works. Okay, in your calculator, make sure that you do some parentheses. You wouldn't necessarily need them on the numerator. Some people use them just to make sure that they get parentheses because it's really the denominator that has to have them in a problem like this. So we've got 0.5 times 70.90 and then divided by, use parentheses in the denominator, 0.0821. Boy, I forgot a zero, so let's do that. Let's go 0.0, that's a decimal, 0.0821. Don't want to screw up R, the gas constant. So 0.0821 times 298 for that denominator. Good thing I was saying it out loud so I could get that corrected. Okay, I've got a density of 1.45 grams per liter when I calculate that. Okay, so we could be asked to do some pretty funky things with our gas law problems, like find density. Okay, here we've got a bubble that's rising from underwater, where the pressure and temperature are 2.3 atm and 18 degrees C. Okay, so that's our initial temperature. We've got a T1 of 2.3. Oh, I was putting the wrong thing. That'll be P1. P1 will be 2.3 atm, right? And T1 will be 18 degrees C. Oops. And we're going to add 273 to make that Kelvin. When we add 273, we should get 291 Kelvin. And then we've got a final pressure. They're going up to the surface. That new pressure is 1 atm. And then that new temperature is 29 degrees C. We're going to add on 273, and we're going to get 302 Kelvin. Okay, so we've got P's and T's. It says calculate the final volume if the initial volume was 2.5. Okay, so V1 we also know it's 2.5 milliliters, but we don't know V2. Now we can use the combined gas law that doesn't have N. So it was P1 V1 over T1 equals P2 V2 over T2. We need to solve for V2 or isolate V2. You could find the equation that has V2 isolated if you want. I like to start from this one, and I like to isolate V2 myself by multiplying by T2 over P2. Now, you wouldn't have to do that. I'm going to multiply by T2 over P2. If you look at your list of equations, you will find an equation that has V2 alone, and it has V2 equals P1 times V1 times T2, and it's divided by T1 and P2. I just like to kind of figure them out myself because it's easier for me to remember P1 V1 over T1 equals P2 V2 over T2. That's something I can remember more easily. Okay, so here's my equation that I'm going to use. I'm going to do T2, which was 302 Kelvin, times P1, which was 2.3 atm. V1 was 2.5 milliliters. P2 was 1 atm, and T1 was 291 Kelvin. So atms cancel, kelvins cancel. We do have milliliters. The dreaded line I get sometimes. We do have milliliters, which is great because we're trying to find a volume. So, gosh, that became a little bit of a mess. I might have to rewrite it. I just want to make sure. I think I'm going to rewrite it so you can see what the V2 was. 2.3 atm, 2.5 milliliter, 302 Kelvin. Over here we had 291 Kelvin and 1 atm. And we got everything to cancel for units except our milliliters, which matches our volume. And when we go to calculate that, always do parentheses around the denominator. Even though that last number is 1, it shouldn't really impact you. It's a really good habit to get into. Okay, and I get 6 milliliters for V2. So again, you could have found your equation from V2 right from our list, but it's easier for me to remember P1 V1 over T1 equals P2 V2 over T2. And I like to use algebra to isolate. But I know there's more than one way to do things. So if you want the list of equations, that's perfectly fine. The next problem says a sample of gas is kept in a fixed volume container. Its pressure is 255 torr when the temperature is 210 Kelvin. What is the pressure of the gas if the temperature increases to 295 Kelvin? Okay, pressure of 255 torr, that'll be our P1. Temperature of 210, that'll be our T1. And then it says, what is the pressure? So we don't know P2. And the temperature increases to 295 Kelvin. That's our T2. Okay, this sounds like it's a fixed volume container. So volume is not changing. Doesn't sound like any gas is going in or out of the container. Number of moles are not changing. So we could use P1 V1 over T1 for our starting is P2 V2 over T2 because we didn't change the number of moles. In fact, we're not even changing volume. That's going to be constant. So our equation really boils down to P1 over T1 equals P2 over T2. Now we want to solve or isolate for P2. That'll be multiplying both sides by T2. So T2 cancels on the right and we'll multiply by T2. So basically P2 equals T2 times P1 over T1. Okay, so our pressure P2 will be our T2 295 Kelvin times pressure 1, 255 torr, divided by temperature 1, which is 210 Kelvin. Now, Kelvin is going to cancel. Torr is a unit of pressure, so looks like we've done things correctly so far. In our calculators, 255 times 295 divided by 210 should give us 358 torr. So temperature increases, we would really expect the pressure to increase. And it's gone from 255 torr to 358 torr. So that makes sense. Sometimes I forget to pause and make sure the answers make sense, but I would really strongly suggest that you do that as well. Okay, here's our last example problem. It says a sample of gas weighs 3.4 grams. At 25 degrees C and 755 torr, the sample of gas occupies a volume of 1.936 liters. What is the molar mass of the gas? Well, if you look back, we had a molar mass equation. Can you find it? It's density times RT over P. Okay, well, let's see what we've got of that. Do we have density? Well, not exactly, but we do have a mass. and a volume. And that is what density is. So we're going to have to do density as mass over volume, and then times RT over P. P. Okay, so that'll work out okay. And then we do have a temperature, 25 degrees C, although we're going to have to quickly add 273 to convert to 98 Kelvin, just so we don't forget. I like to do that right away. And then a pressure, we do have a pressure of 755 torr. But we're going to use R. And R's unit of, we've been using R, 0.0821, with a pressure unit of ATM. So we probably want to get out of torr right away. Let's do that. Let's go, okay, we don't really want to be in torr. So let's put that over 1, 755 torr. Let's bring down torr and change those units to atmospheres. In 1 ATM, there's 760 torr. Okay, so torrs cancel. We want to convert to ATM. When I calculate that, I get 0.9934 ATM for that pressure. I think it'll be much better to have that pressure in ATM. Okay, so my molar mass is going to be my mass divided by my volume, so 3.14 grams divided by 1.936 liters times R is 0.0821. I really like to do liter atmosphere over mole Kelvin. A big reason to do these units is you can catch yourself. If atmosphere and torr is not canceling out, that'll be your sign. Oh man, I need to change those units. I'm at 298 Kelvin divided by, again, I know now to put 0.993 for ATM here. But let's just say I was writing 755 torr. If I was doing that, if I was sitting here writing 755 torr, because that's a really common issue, and I would go, okay, liters cancel with liters. Kelvin cancels with Kelvin. Okay, those are gone. Gosh, a density is going to be grams per mole. Great. Okay, ATMs cancel with torr? That doesn't cancel. That's your sign, like to go back and do this conversion from torr to ATM. So we already did that conversion. So we know that we're actually going to put 0.9934 ATM here instead. But my point is that leaving all the units of R is key to getting units to cancel, and that's key to noticing if you've made a mistake. Okay, so again, I wanted units of gram per mole. Why? Because I'm calculating a molar mass. So I am going to do all this in my calculator. If I did it all at once, I do this whole numerator, I do parentheses, and then I would do this whole denominator. So 3.14 times 0.0821 times 298 divide, make sure you do parentheses before 1.936 times 0.9934 end parentheses. Those are really important. And then when I calculate all of this, hopefully I get a final answer of 39.9 grams per mole. Wow, beautiful. So hopefully now you are feeling much more confident about the ideal gas law and combined gas laws and how to solve gas laws problems with them.